to talk about what does it mean to optimize application performance, right? Uh, so I've already covered a bunch of things here already. I'm interested in psychology, engineering, percussion, and I really like a pretty old game now. It's called Age of Empires. It's been what 25 years, I think more now, and it's a super interesting strategy game where you have to zoom in at the same time you have to put a macro game. It's a good combination of how even life has to be. Like you have to focus on the details, but at the same time keep an eye out on the larger horizon. So I really like that game. Yeah, so today's agenda is I want to talk about application performance from understanding of the workload. What are we running? And then how do you optimize the performance of the app or backend or whatever system in general? What does it really mean to be something to be scalable? Is there a formal method for defining it and whatnot? I'm not myself into a lot of math like Vipul is, for example, so I won't be able to go into deep into math, but I'll come about it from a practical angle, which is some of the production use cases that I have solved personally, and I've seen some of the other team members in 1 2 have solved. So we'll cover touch upon that. So that's the overall agenda for today. So I want to like start with a question or just open some discussion points, right? So imagine your program, you joined a new team, you are given some program, and you run it, and it says okay, it takes 2 hours to run this program, and that's about it. All you know about it, like there is some machine where this program runs. It's like almost like a black box. You don't know what's inside, what does the program do, etc. And it takes 2 hours, and you are asked, okay, how can you make it faster? You want to run it much faster. What would be the first thing that you would be able to do, given that's the limited information? And so I want you to sort of think. I'll take a pause here, and I really want to have some inputs from all of you guys.
We'll throw in more resources.
Fair enough. Yeah. So we throw in more resources. Like if we don't know what the program does, the only thing that we can do is, well, probably provide more CPU, right? So some more like and see if it works. Then you provide more maybe RAM and see if that improves the performance. You basically provide more and more the classic 3 or 4 types of resources. You have CPU, you have RAM, you have network bandwidth, and probably better disk. If it's very CPU intensive or typical type of program, you may even run it on GPU. That could be another thing that you would do. And imagine you do all of that and you realize that let's basically double the machine size, essentially like Moore's law in some way. Let's double the size of the machine, and we run this program, and then now it runs in 1 hour 44 minutes. So it's about 16 minutes of improvement from the previous 2 hours of time. That's probably what 12, 13, maybe 15%, let's say improvement max. What you realize though is after you double the machine again and again, it doesn't really get better. So, for example, what did we do here before we move on to that part? We did vertical scaling, right? Like we basically added more hardware, and it's like a single machine. We increase the resources on that machine, so that's like vertical scaling. And if we further double these resources, we further kept on saying, okay, let's run it on even bigger machine, even bigger machine, even bigger machine, right? At some point in time, what you realize or what you feel is that what you see is that no matter what you do, the program doesn't take less than 1 hour 36 minutes, right? So this is where no matter how much compute, disk, memory, CPU, whatever you throw at it, it will still take this much time at a minimum, right? So what do we do at this point? We still want to improve the performance. Any thoughts?
Um, so we have some discussions in chat. Anubhav is saying we can run perf and flame graphs. This might give us hint what exactly is consuming more CPU.
Oh yeah, cool. Perf and flame graph, cool. Double compute exponential cost. Yes, that's also another point. So here we almost assume that there is no implication of cost. Uh, one option one might think is that okay, what if we run it on multiple machines, the same program, right? Will it be faster? So you try to do that. Uh, so this is what we spoke about. That so the slides animations are a bit bad. I need to fix that. But yeah. So you decide. Let's say let's run it on multiple machines, horizontal, right? Horizontal scaling. Now, without knowing the program, here is a question. Without knowing what the program does, is it possible to just run it on multiple machines and expect it to be run faster? No, right? Like, yeah, if it is stateless, correct, right? So that's a very important point. That we don't know what it does. So is it possible to formally or informally, whatever, just guess? Even the answer is probably no, right? We can't really know whether if it runs on in 1 hour 36 minutes on one of the machines, even if you run it on multiple machines, it's just going to take the same time typically, right? So even if you run it on whatever hardware and run it parallel, but it still takes that much time. So now at this point, we have to improve performance. Obviously, the part that you guys talked about is perf and playing graphs, etc. More getting into the details of the program, uh, and still how do I say, looking at it from outside, not really opening up uh, the details. Yeah, so someone says, how are we modeling the inputs to the program, right? So this is where we really want to understand what the program does really. So for now, let's assume that we kind of open this black box and we see what's inside, right? So what we see is that the program is something like this. Like what we're trying to do is we have a big Wikipedia file, uh, and we are trying to parse the XML. Imagine we are taking a Wikipedia dump, which is in XML format, and its dump size is about 40 GB or so, right? And we're reading that file, we are parsing the content of that file, and we are counting the most common word used in Wikipedia, right? So if you go on any Wikipedia page, you traverse the whole graph, you end up with a bunch of HTML pages. Imagine you convert this into XML, you get the raw text out of it, and you start writing, you pass the program, and you run basically word count on that, almost like a map reduce kind of thing. And you would end up with what's the most commonly used word in Wikipedia, right? So if the program was supposed, it was doing that, and that's why it's taking so much more time, right? So how do we now if we know this, then what can we do to improve the performance? Yeah, now profiling makes sense. Yeah, so we know we can look at, give it some input, and then see, run it for that time, and we see, yeah, split the input and distribute the workload. That's another good suggestion. uh, Shard it and merge the results, classic. Parallel execution, add threads. Deepthrough says, add threads, make every thread count one chunk, right? So you're all sort of getting there. The idea is that now we want to break this problem down. So right now, one of the other thing that you discover about this program, that it is sequential. So it's a single threaded. It just starts and does this in a sequential manner, which is where it's taking so much more time. Right now, first thought that comes to your mind is, okay, let me add some threads. Let me make some different points of execution. Typically, then uh, you would like want to do something like this maybe, where you spin up threads, and you want to read multiple files in parallel. You want to break if there's a single file at the input, you would want to break this into multiple sub files and whatnot, right? So let's say what you do is you break the program down into separate functions, like almost high level like functions here. One is the reading of the file, then parsing that content, and then counting the frequencies, right? So this is somewhat sort of logical like grouping that you create, and then you're going to run this in multiple threads or whatever, right? Now these are types of workloads that you are going to run. One question here that you might encounter is, do we do parallel or concurrent? So again, I think I'm sure all of you by this point know the difference between parallel versus concurrent. There is a really good talk by Rob Pike and bunch of others, and I think everybody has now adopted that good single line sentence about differentiating between parallel versus concurrent, which is concurrency is about is dealing with multiple things, right? And parallel is about doing multiple things at once. So we have this original program which is, let's call it monolithic, in a sense that it's a single program with single thread with no function separation. It just like reads the entire file, passes the token. Imagine this to be written in any programming language, a single big giant function, right? And we want to break this down into some of these three high-level functions. We This is probably like we could debate on whether these are the right functions, the right boundaries between them, and the interface and whatnot. But for the lack of, from a simplicity point of view, let's say we start with these three functions, essentially, right? So we would be able to run these into, we break this program down into some sort of a pipeline of sorts, data pipeline, right? Where you read the page, you maybe use some sort of a queue in memory queue where you put producer consumer pattern, for example, where you would parse the page, you would have another go routine or whatever, or some sort of a thread, for example, to be able to count this. This is how what you're trying to do is you're trying to break the single monolithic program into separate units of computation, essentially, so that tomorrow, right now, they would still run on a single machine. But if you split them in a certain way, with the hope that or with the goal that you can even split parts of the component out into a separate execution. Okay, so your in-memory queue can become a separate distributed queue, like RabbitMQ, Kafka, or whatever, right? Where you would do a producer-consumer message passing. You could even go in an actor model way where you would pass messages across these three actors, stuff like that, right? So what you're really trying to do is create a mental model of a program where a single monolithic execution can be separated, and each of the parts can be run independently almost of sorts, where each of the parts interact with the other parts via some common API interface or common data value objects, essentially. Right? Is so far everybody with me? Like any points, questions? Okay, cool. So this is where we reach to, like I'm taking a segue here and reaching into Amdahl's law, converting a legacy non-performant. Yeah, correct. Thanks, for yeah. So, how many of you don't know? Like, I'm not sure. Have you covered Amdahl's law? I guess as part of the previous thing. If yes, then I can quickly skip over this.
Yes.
Okay, cool. So then I'll just quickly do a quick brush up. Essentially, this is what we have, right? Like a 20 hours, imagine 2 hours or whatever. So essentially a single threaded process, and in the animation we need to work on it. But this is some part of the program that cannot be parallelized. I think the unit has to be a bit fixed, but ignore that for now for me. So what we're saying is some part of the program can be parallelized, and some part, this is a sequential part, which cannot be parallelized at all. That means no matter what you do, you are not going to be able to run the program, no matter how much hardware you throw at it, in less than 1 hour. right? It's always going to take 1 hour for the sequential part, which cannot be parallelized. And then this remaining part can run on any supercomputer and it can be done in like milliseconds, nanoseconds. But it still will take some finite, minuscule amount of time, right? Which is where Amdahl's law talks about literally like having you break the program into parallelizable parts and non-parallelizable parts, right? And thus, efficiently you break the program algorithm into parallelizable and non-parallelizable, that will make your performance much more faster, right? Then you can actually utilize the correct type of resources, whether it's CPU or IO or memory or disk or whatever. So I won't go into the formula here, but similar to that, a general case of Amdahl's law is universal scalability law, right? Where it talks about the same, like imagine again a single program where this part is a single threaded process, meaning this cannot be parallelized, the yellow or whatever portion cannot be parallelized. And these parts, this part of the program can be parallelized. But at the same time, there is inter process or inter thread or inter process essentially communication where there is some contention, there is some data that has to be exchanged between these parallel parts. Like they cannot be run independently in parallel. They have to do some message passing. They have to synchronize on some common data structure at some point in time, or they have to share results. For example, in case of MapReduce, the mapping phase can be infinitely parallelizable or embarrassingly parallelizable, but the reduce phase then funnels everything down into typically a single reducer, right? You can even have multiple sub-reducers in the sense that each machine, if you imagine this to be like a Hadoop or a MapReduce, classic MapReduce, each machine can do its own reduction in some way, and then there is a further reduction of the reducers. But it still ultimately funnels down into a single reduction at the end of the day. So there is some inter-process communication, which is where universal scalability law talks about how do you, because of this contention of between these two processes, what you do get is that you expect as the number of CPUs goes from the y-axis here is the speed up that you expect, and the x-axis here is let's say number of cores or CPU, or imagine to be like the machine spec. So it's 2x the specs, 4x the specs, 6x the spec. Right? So it's like increasing in exponential manner, doubling every or adding like 2x the spec essentially. What you would expect in ideal world is like this kind of a graph where as I add more machines or more CPU, more RAM, more resources, I should expect a linear performance. But what you do get actually, if your program elements and your algorithm is such that it requires contention between even the parallelizable parts, is going to be slower than what you would otherwise get using Amdahl's law, right? I'm assuming final reduction has to be blocking. Yes, that's correct. Thanks. So far with me, is it too fast or are you guys following? Give me some sort of a nod or any questions. Feel free to interrupt me with questions. I'm okay to take questions in the middle of the presentation also. Correct. The takeaway from this graph is an interesting question. The takeaway from this graph is that typically we required to do some analysis for capacity planning, right? So this kind of graph really helps in planning the capacity. I'll cover one of the use cases where we put this into effect. So that's the kind of purpose of thinking about this graph in terms of if we were to do a capacity planning for your hardware, saying I want to, one machine can handle like 100,000 users at a time. I want to be able to support 10 million users. How many machines do I need? If that's the kind of calculation you want to do from a forecasting, budgeting, etc. perspective, this kind of logic and thinking would be really useful. So that's where we are studying or we're thinking about these two laws, which are practically applicable for our case. Hopefully that answers your question, Anubhav. So ultimately, we have two types of workloads, if you think about it. One is the CPU bound, and other is the IO bound workload. Uh, some examples of CPU bound would be, one would be if you want to calculate digits of pi, right? Like you want to calculate what the value of pi to a millionth degree accuracy, right? Precision. What would you do? So other could be, for example, for IO bound, an example would be you want to grep a word, which is what kind of we just discussed about Wikipedia. Instead of just grepping the word, we are really counting the frequency of the words. So grep has a -c option, which actually gives you the count of the word, right? Essentially. So this is predominantly like IO bound workload, where you're reading 40 GB of data to be able to find a single word and the number of occurrences of that word, for example, right? Whereas calculating digits of pi, there's typically some mathematical like algorithm that you would use to simulate something, and then there is no IO involved essentially. In so what I want to do right now is take one example of a CPU bound workload, especially like calculating the pi essentially, right? So I was thinking that is there a possibility to have, for example, let me go back. Is it possible to devise some algorithm that calculates digits of pi which can be parallelized? What I mean by that is I want to distribute the computation of calculation of pi across various machines such that, let's say, each machine gives me either an approximation, or I can say almost like MapReduce, where imagine I have 10 machines. I say, okay, first machine, please calculate 3 point, like the next 10 digits of pi. Then the next machine, I say, calculate the 11th to 20th digits of pi after the decimal point. Then the third machine, I say, calculate 21st to 30th digit of pi, and so on and so forth. So if I were to create some sort of algorithm like that and distribute my pi calculation, then I'm going to be able to get the first 10 digits from one machine, the next 10 digits from other, and likewise. And then I can, if I want a million precision and I want it in whatever 10 seconds, and I know each 1 second these many computations can be done, then I can estimate how many machines I need, or what's the CPU memory utilization that I need to have, right? Are you following so far? So does anyone know of such algorithm? Like, is there any algorithm for calculating digits of pi that can be parallelized? Have you heard about anything? Okay, so Amir says Monte Carlo. That's exactly right. That's pretty interesting. Like, actually, I did not know about this. I discovered this while thinking about this. Okay, I googled for it, and then like, okay, there is a Monte Carlo method, which is even more insane than what I had thought of. In a sense that Monte Carlo is infinitely, or is embarrassingly parallel. These are the type of algorithms, or type of programs which are called embarrassingly parallel. What does that mean? So the way it works is, imagine this to be like a square, and 1 by 1 square, and then you have a pizza, or a circular sort of pizza type shape. And what they say is, okay, imagine you're throwing darts randomly on this, right? And then some darts will land on the pizza, some darts will land on the outside of the pizza, right? And if you do this enough number of times, if you run these iterations like millions or trillion, whatever number of times, then the number of total darts that you throw versus the darts landing on the pizza, that kind of ratio you're going to get this to be pi by 4. So with that, you can kind of calculate pi. And the best part about that is this simulation of random numbers, etc., can be done on any computer without having to depend on other computer and other sharing the resources, or doing some interprocess communication. Right. So with this, these are kind of embarrassingly parallel in the sense that you can literally like Amdahl's law to the fullest, in a sense that there is no contention between two parts of the algorithm. And if you run this, then you get like this kind of simulation where uh, some of the you calculate the number of points and you calculate the number of red points and blue points, and then divide the ratio, and then you get some number. And each machine can do all of this in parallel. And in the end, there can be, you can think of a reducer phase where you can combine the total red points and total blue points and then get a really nice long approximation of pi, essentially. Right? So this works for very CPU bound workloads. Um, so I'll just take a sort of pause here and talk about what have we done so far, right? So we started with thinking, here is my program as a black box. I want to make it faster. What are my ways? One way we talked about is running more on a better hardware. That's vertical scaling. Then we said we want to break this into multiple machines because there is a limit in terms of how much hardware we can scale. And that's where we said, let's do horizontal scaling. And we did a bit of horizontal scaling. For that, we realized it's not just dumb. If it's not stateless program, then you can't just run on multiple machines. You have to really open the program, see the parts, remove the state from it almost, and only the non-stateful parts can be parallelized. If at all, they're more useful that way, right? So, oh yeah, okay, nice. Uh, so this way we are able to think about and we looked at the Amdahl's law and universal scalability law in terms of how does it impact our application performance, or how do we need to really think about our workloads, right? If it's a CPU bound workload, no matter what kind of disk or IO or whatever you throw at it network, it's not going to be useful. Similarly, for IO-bound workloads, the more CPU you throw, the more threads you are, you may not really benefit. Like you need to get a different way of handling IO-bound workloads. Right? Some of them are for IO-bound, you can use like faster storage devices, so NVMe disks and whatnot. Then even like improve network speed, because typically if you're across distributed systems, then network speed becomes the limit in some ways, and you can use caching at various levels. You can optimize data access patterns so that you don't access, like almost put compute where the data is, which is what a lot of big data tools do these days. That instead of moving data around, they move compute to the data, right? That's kind of thing that you can do. You can do data compression and stuff like that. So that's your sort of way of thinking about application performance from various angles, like typically from CPU bound to IO bound, and then breaking it down into various subcomponents and figuring out how you can make something more parallel, whether you can benefit by adding more threads, or you would rather benefit by increasing a particular part of the hardware and whatnot, right? So that is kind of what I had for today. At a In the real world, we kind of go between these two. Some workloads are more IO bound versus CPU bound. Some workloads are not so. And we have to really take a call based on what is the type of workload and analyze it essentially. Right. So that's from the presentation, like what I prepared, I want to take about two use cases at this point. Like there's a different recent talk that I had given. I can sort of take up a two use cases based on that. And this, I think, would be more related to not just the theory, but what are the practical applications of it, right? So if I can, if there are no questions, then I can kind of proceed with these two case studies essentially. All right. Cool. So one interesting thing that we had to do, as I said, there was a question from Anubhav, I think, right? What's the takeaway from the graph? This is kind of related to that. Uh, we had a use case of building a SaaS APIs. So imagine this to be like a eKYC SaaS API where you have machine learning models where uh, they are accessible via mobile SDK to B2B customers. Uh, Imagine, for example, you go to get a new SIM card, right? And you would walk into a shop, and the shopkeeper says, "Okay, I need your Aadhaar card, I need your photo," and they open their mobile app, they click your photo, they click your photo of your Aadhaar card, and they do some sort of a face matching, right? There may be a optical character recognition where if they click photo from your Aadhaar card, they can read your name, date of birth, gender, and address, and other details, right? So these are run on machine learning models. So we had a couple of models. One was for face detection or face matching. Other was for live face detection. Other was for OCR and stuff like that, right? So imagine these models are are given to these consumers, the B2B customers, via some sort of a mobile SDK and backed by APIs. So we built these SaaS APIs, and then the SDK would call these APIs to be able to do uh, face match and image recognition, right? And this needed to scale to like 2 million requests per day. So we would get about 2 million plus more API requests for machine learning models per day. So typically, imagine again, this was for a large telco and banks and insurance in India and other regions. So as soon as the store opens, let's say typically at 11 a.m., you would start seeing massive spikes. During lunchtime, typically 2 to 3 p.m. usually was the lunchtime, you would see again some dip. Again, evening was the highest rush time when we would see so many requests at the same time, right? So that's the kind of API and scale that we were dealing with. So how did we go about this, or what were some challenges or problems that we ran into, right? So before that, we kind of have this requirement that we have to give some sort of a SLA or SLO essentially that hey, we will commit to having 2 nines of availability. At least like during the business operation, it was even more critical. But overall, it turned out to be okay. 2 nines of availability. We need to make sure that because these models run on GPUs, we need to have cost efficient, and we need to have auto scaling in place in somewhat sense to be able to handle peak loads and whatnot. And we had set ourselves a modest target of like less than 5 second API for API latency for 98th percentile. In theory, like we were able to give much more better numbers, but this is the worst thing that we had committed to the customer that we will have these for 98th percentile at least, right? So how did we like kind of architect it and what we had done, right? So there was a client SDK which would talk to the NLB, and this is the API layer, which is the SaaS API layer for eKYC. Um, for every request from the SDK, for example, there is an image upload or there's a face match or a face recognition request, we would send the machine learning models would be running on these workers. They would use GPUs, and you would get a request in RabbitMQ with the payload that okay, here is the 2 images which we want to match, and then this is going to run the model on these 2 images, and then update the results in database and blah blah blah, right? And then the response is sent back to the user. So this was synchronous in a sense that user would wait for it to get the response, but internally we had tried to add a queue to absorb any shocks or absorb any immediate spikes. So that was the purpose of the queue. So internally it was not completely asynchronous. From a user point of view, the flow was still synchronous, right?
Uh,
So yeah, go on, please.
Chinmay, I have a question. Can you go back on the SLO slide? So yeah, so for everyone, I think this is the question that how do we come up with these numbers as a distributed systems engineer? Is it always a business requirement, or how do we come up? Because before
Yeah, yeah.
designing system, how do you understand that these numbers will be okay?
Correct. So this again more collaboration with business, and in some case we had to like if you talk to business about what is the availability that they need, they're always going to say 100% because they do not know. They cannot talk to the customer from imagine a sales non-tech person saying, "Oh, we are okay to have these many failures." Uh, So that's where there is some education or education that is needed from a tech SRE point of view to the consumers also or to the business team. So it was done in collaboration with them, and some of it was done after the fact also. So this is where we did a bit of a pilot for the first 3 to 4 months, where we said, look, we'll launch this and see how it goes, and then based on that, we'll come up with here is what we can promise as our availability to you, right, in the contract or whatever. So this is hopefully that kind of answers your question. And we did some like we asked our product team to do some surveys to the existing customers of the, like for example, go into stores, check with people what their current experience is like, and most of them said, yeah, it takes currently like 10 seconds or more, and we're still okay with it. So we gave like less than 5 seconds as API latency, and that they were happy with essentially.
So like you legitly went to a physical store for the last one?
So our product managers did a survey. We had an anonymous survey and whatnot, and we said, okay, look, here is what the market tells us, and this is what we can do.
Interesting. Thank you.
Yeah.
Chinmay, I have there's a lot of literature available on SLO and SLA, right? But very few literature available on costing part, right? And I read a lot of these articles where the cost generally for startups, right? The biggest problem they face after a while is the cost, right? Running on AWS and all these clouds, right? So, I mean, what factors are, I know this is a very broad question, but how do you make sure that even when we're initially setting up something, right? Especially a startup or something, how do you make sure that you have your cost in what do you say, control, right? Or over a period of time, how do I keep track of the cost, right? I'm taking a design decision, right? Uh, say and this, how does this impact the cost on the longer term? So some of these things, how does it start to determine?
Correct. I think that's a very important question, and this is where the whole capacity planning helps us, and which is what I'll cover in the second problem. So hopefully, like if that doesn't answer by then yeah, please interrupt me again. So I'll sort of move on. I want to hopefully this architecture of the flow, if it is clear, then I'll move on to one of the problem that we face related to the back pressure, throttling, stuff like that, right? And why that problem happened. And then I'll talk about the cost part of it, which is very important. So how learning about universal scalability, Amdahl's law, etc., really help, right? So this was the idea, and also in terms of cost planning. So we did a load testing on a single GPU node to find its throughput and ensure max utilization. What does that mean? So we say, okay, we have a single GPU. How many face matching or how many OCR requests can it handle? What's the if I use it 100%, if I ensure max utilization, what's the speed of the car essentially, right? Can it go 120? Can it go 160? If I just keep pressing the throttle full on, right? And we've kind of find that max number that okay, it can do 15 or 25. I think yeah, I mean whatever 25 OCRs within that RSLO period. So less than 5 seconds, 90th percentile. This is the number. Like these are the number of API requests or model runs that we can do per second or per minute. Right? So you find that kind of a unit economics for a particular GPU node. You know the cost of that GPU node then, and then okay, this is a separate part. I'll skip this. We also did bunch of failure mode analysis saying uh, if any of these parties fail, then what happens to the rest of the ecosystem and whatnot. And end-to-end observability, okay, that's separate. Okay, the autoscaler is again separate. Yeah, so first, like I want to talk about this issue that we ran into. We were using Nomad at the time, and we realized that it cannot run multiple worker containers on the same GPU node. Meaning, what does that mean? So we have a GPU, and we want to run multiple Docker containers or workers on a single GPU because there is enough RAM and there is enough cores on a single Tesla T4 GPU. But the way Nomad scheduler works is that it does some sort of a pinning to the GPU, and it won't allow other containers in the same same VM of sorts to be able to use that. So you couldn't run this using Nomad. So what we ended up doing was we ended up doing Docker Compose, raw Docker Compose, and raw Docker exec using Nomad. So the Nomad was still used as a scheduler, but we were using Docker Compose up as part of a Nomad job essentially. And that was a limit with Nomad, so we kind of circumvented that. And that straight off, we could run four sort of workers on a single GPU machine essentially. So that literally like 1/4 our cost. So earlier we would have $100 an hour, whatever. Now we would have $25 an hour. That kind of something that we had to find out and fix. This is still an open issue on Nomad, and that's the solution that we recommended. And a lot of people still like we just use that solution. And so this is again how technology and the cost kind of play into effect. Other solution or other issue that we ran into was something interesting which I had written about also a while back on I think one of the Twitter threads. So we were seeing 25 seconds or more response time on the SDK, which is kind of clearly like violating or going to violate our SLAs because we had less than 5 seconds, right, for 98th percentile. So as this time went up, we were worried that this would go crazy and we would go out of our SLAs and then have more problems and whatnot. So the challenge was that there was no queue depth. Typically, when you add a queue, you see that why is there a latency here? Because there is usually the workers are the problem, right? Typically, we have seen machine learning workloads take time. If there is a massive spike, then for these workers to be able to consume these jobs and return response is going to take time. So we should see ideally some depth in the queue, that lot of unprocessed jobs, right? But we were not seeing that. And the latency at this level was pretty okay. So we were really not sure why is there such a high latency on the API side though, even though workers are not slow. So there was no processing lag on the workers. Why are we seeing still such a large response time? Turns out that here in the API layer, there is the way the interaction worked was API would send a message to RabbitMQ. Workers would read the message from RabbitMQ, process, and return the response back to another queue, which again, there is a go routine, separate set of go routines which read from this RabbitMQ and then update the database and return results to the user and whatnot. Okay? So the number of go routines that were doing this was just 5. And based on our extensive load testing and whatever, we had concluded that the API layer doesn't need to scale that much. So we were just running 3 to 4 pods for API, not more, right? But then this is where the contention really happened, and there was not even a CPU utilization issue or memory or whatever. It's just that the number of people who were handling the response, or the number of go routines that were handling the response, that was just limited to 5. So this is where the back pressure started piling up, and then that's why you saw the API latency increase. This took us quite some time to figure out this issue. Again, a bit of a lack of end-to-end observability, let's say, or even a preconceived notion that the problem has to be at the worker level and not anywhere else. So we just spent a lot of time looking at something that wasn't a problem at all. After we fixed this sort of went normal, and we got the normal response. So there are other like things that we did not cover, but these are some things that we ended up like using in this health skip. This is from other. Any questions about the previous case study and the question on the cost? Is it clear, or should I sort of explain more on the cost part also? How do you calculate and project costs? Yeah, I wrote a thread about this a while ago.
Chinmay, can we go back to the failure mode analysis that we skipped over? Because I'm kind of interested in how you went about doing that.
Yes. So, okay, maybe I'll spend a bit of time on testing, right? So I think distributed systems testing is even a even bigger challenge. Like how do you really test the failure modes,
Yeah.
right? So what we had done, and despite this, we saw the bug and we were like, okay, there's so much of more that we could have done further, but given the time and the launch and whatnot. So here are some things that we had done. We said that look, I need to test each of the components in isolation to make sure that it can handle the load. For example, we're looking at 2 million API requests per day. So what's the maximum peak that we are going to hit in terms of API request? So let's just call that API. That API doesn't do much. It just writes a no op or whatever. It doesn't even talk to any other system database or whatever. You just mock all of that, but make all those calls, right? Then similarly, you test ML workers themselves. Like we said, imagine I have a RabbitMQ or I have a way of triggering machine learning workers where I just bombard them with like 50,000, 100,000 requests, and then there's only one or two workers, and notice how much time it takes to process all these requests. Right? That way, I can kind of find out their throughput essentially over a long period of time. Then for the third party like RabbitMQ, we were using Minio, which is S3 equivalent for image storage and whatnot. We were using Postgres, Redis. These were some components that we had more confidence that these are sort of third party and components and proven boring tech that has been used for quite some time. So there is not much need to test their scaling, especially for the scale that we were at. But we still tested some of them, like for example, RabbitMQ specifically, because in the team there was not much comfortable with using RabbitMQ. So we did test writing a simple consumer and a producer where we just bombard RabbitMQ with so many more messages and we just write a consumer and see if it can hold up, right? With the infra that we were thinking in production. So this is some sort of isolated unit testing of components. That's what we did. Later, we also did end-to-end unit, end-to-end testing in some way at a load level, where we said, look, let's run the entire component on staging, APIs, ML workers, Rabbit, Minio, Postgres, Redis, everything. And we have these a few set of images which we have pre-uploaded, and we bombard the ML workers and the whole thing with sort of JMeter or whatever load test and see what's the latency like, what's the response like, etc. This test itself was very costly because we would have to run it. Imagine every time there was a new machine learning model, we had to do some sort of load test to make sure that the new model doesn't slow down the API response, right? So this meant rolling out new changes means we have to spin up a bunch of infra. We have to run the load test for a decent amount of time to be able to see. We have to compare results from past load test to this load test to see if there is not a massive difference in terms of performance, throughput, latency. It meant a lot of kind of work. And somewhere we kind of work with the ML model team, data scientist team to know what they change, and we would take judicious calls saying, okay, this doesn't need to be load tested because it's a very small change or whatever, and we would only do load testing once in a month and stuff like that. Because the cost of doing that load testing itself was in about $1,000 or whatever, right? To be able to reliably say that okay, we can actually we are super confident that this model or this new model will not cause any performance issues, right? So this is more around how you do failure, like how you analyze what could be the failure modes. We also tried, for example, things like in RabbitMQ, we tried taking down one of the nodes. We were using a distributed cluster, so we took down one of the nodes while in this traffic. See, it doesn't have any impact on the output. Similarly, for Postgres, we had a master slave kind of setup, so we took down the master, saw during staging what happens, stuff like that, right? But the idea is that yeah, the more you do this practical testing, the more cost it's going to incur. So you kind of have to balance this essentially.
Okay.
Hopefully this answers.
Yeah, that answers my question. I did have one quick follow-up question, if that's okay. So we were discussing
Yeah.
like cost of all this infra, right? Is it more typical now for infra teams to do a cost exercise of seeing how much hosting this stuff on cloud infra costs versus hosting it themselves?
Yeah, so I think this has to ideally be done much before, not when you're going to prod.
Yeah, of course.
And
But
again, this really depends on what scale or what are you really, yeah, what are you getting into? Essentially, it comes down to this, like if the total cost of ownership, right? Like if my uh, cloud costs as a day-to-day cost over a period of 1 year or whatever, versus if I do upfront leasing of these resources and then have my team engineering costs to be able to build similar set of abstraction on cloud or whatever, then it's really finance plus tech kind of decision. In most cases, I still have seen it's especially again, it's a very like I won't want to give a generic advice, but let's say typically for a 1 to n kind of a startup where you're growing from 1 to 10 million users or whatever, it still may be a good idea to go with some cloud, right? Because you don't know whether you are actually going to scale, right? And when you do scale, you can kind of throw more hardware and get by till that time. And as you really scale, have a massive economy of scale, then you can really think about, okay, what parts of it make sense to host myself. The classic for that would be stateless components. Any stateless components, you can host it and move them and package them somewhere else much more easily. Stateful becomes much more harder because then there's state involved, you have to migrate, you have to do backup and what. So not sure whether yeah, I'm able to give a clear answer, but yeah, it depends is a standard answer for that.
no, that's okay. That answers my question. Thanks.
Chinmay, I had a follow-up question on this only. So, if you see the recent trend has been to move the workloads on AWS at least, the ARM processes like Graviton and all, right? So,
Yeah.
so I mean, do teams typically do an exercise to decide on the infrastructure, saying that, say, if I want a GPU workload, would it be the best processor? What would be the most suitable and the cheapest processor? Or what would be the kind of RAM that I would need, right?
Yeah.
So, yeah. What is IO? So
Yeah.
do teams do that?
Correct. Yeah, interesting. So we have to do it. Ideally, at some scale, you end up doing this. So, for example, there was a recent again thread that I had written about Victoria metrics, where we were running what 50 plus nodes of Victoria metrics, which is a Prometheus kind of metric storage, right? So that cost was $10,000 or more. Now we wanted to save that cost, so what we ended up doing was, okay, we knew that Victoria Metrics runs on specific, like runs better and faster on specific type of CPU architectures or machines. Like it has to have more like compute heavy resources for VM agent versus CPU heavy, so the whatever the memory heavy resources for VM storage and stuff like that, right? I forget exact dichotomy, but there are, it's kind of written in the documentation, or we have to, if you run it enough number of times for long time, if you maintain it, you know it that okay, this actually runs better on this type of hardware. So then using that particular hardware and having mechanical sympathy for it really helps at scale, because that then runs the software much faster, smoother, and it also takes like good performance and cost trade-offs. For typical general purpose APIs and whatnot, I don't think this matters that much. But for specific type of workloads, maybe databases or even like machine learning models for sure, for example, right? These things matter, and then optimizing the type of hardware would really make sense. For example, in our case itself, we evaluated 2 GPUs and we ran the same kind of load test way back, right? We had one Tesla T4 GPU, and I forget the one that we otherwise tried, but we ended up finalizing Tesla T4 because it gave the best cost plus performance trade-off. Again, the way we check it is have one Tesla T4 and one other type of GPU, run the model, deploy the model in same, bombard it with same number of threads, requests, etc. Measure the performance over like 1 hour. Okay, in 1 hour, this T4 can do 1,000 requests. In this can do 820 requests. And the cost and whatever difference is this much. So which is the best GPU that we should use for our use case, right? This is the kind of exercise that we had done. And then we finalize, okay, Tesla T4 makes sense. Let's run this on this one.
Nice, thank you.
Yeah, I'm not sure how much more time we have. Otherwise, I can skip the second problem because we're already like 1 hour.
Yeah, we can skip the problem. I have one thing to add here on the PR which you showed, the open issue which you showed.
Yes.
This thing, this is a harder problem because not like CPU, or at least earlier, when you opened it, I think it is from 2019, I guess, right? 19 or 20. So at that time, GPU, you cannot use a fractional GPU. So one job will hog the whole GPU. Now there is a latest development. NVIDIA has come up with MIG, multi-instant GPU. So you can actually divide your GPU into fractional resources, and then you can use one GPU for multiple jobs. But again, it's not as easy as a CPU. It is like even if you see how the division is happening, the division itself is very complicated. So I just wanted to bring that up for everybody if anybody is interested.
Yeah, makes sense. And I think this also was not a problem with GPU as such. Like this was a problem with Nomad, the scheduler. Because with Nomad, we couldn't share the GPU. But if we ran Docker Compose or raw Docker exec driver, we were able to share it. It was just the way Nomad was doing something funky with pinning a GPU with particular job and whatnot. That's what had to be fixed. So we just ended up using a workaround, which is use raw Docker Compose inside of Nomad, because we didn't want to change your scheduler to use something else. Because a lot of other components, for example, all these components we were deploying using Nomad. So just for deploying this, we don't want to have another set of thing. So we just said, okay, for deploying this, we use Nomad, but underlying, instead of using a simple Docker image, we would use a Docker exec raw driver. That way we can run a multiple Docker containers on a single GPU node.
Right.
Then that will do a load balancing or routing of, or it will share the GPU resources, RAM and the GPU itself.
Chinmay, one more question. Sorry, I'm asking the last question.
Yeah.
So you have been working there is a lot of excitement around this like ML infra, right? And the example that you showed was actually an instance of running ML workloads, right? Apart from the GPUs, what are the other things that are typically different in ML infra than say normal infra, workload infra? I mean, what are other things that you need to care about?
It's a good question actually. I haven't had major exposure to LLM or GenAI type of ML models, like to be able to host those, or even the whole open source, recent open source models, etc. But the whole challenges that I've seen are like GPU is one challenge. Other is the packaging of the models, the Docker image size, then how you version and history of the models that you maintain. One of the things that maybe again a more SRE infra related problem, not much of a programming related problem that we ran into, was that the data scientist did not like the way they were doing versioning of ML models, right? Was that they would have various pickle files in various date-wise folders. And all of these pickle files across all of the dates are mounted in Docker. And our Docker container size would grow like crazy. Like it would be 14 GB container. And we were like, why are we running 14 GB of container? It's going to take like 10 minutes to pull that container or 5 minutes to pull that container on an image and then run it. And it's just insane. Why do we have so much of a image size for Docker, for that Docker image? So they were like, oh no, we wanted to dynamically change what models do we refer to and this and that. And we had to then talk to them, how often do you really need to do that? Have you ever had to do this in production? Not, then why do we have to do it this way? Can we not maintain just last two versions instead of maintaining like all the history from like 6 months ago and whatnot, right? So I think the model drift is around that we talked about as well. So this is where we then cut down on the way we ship the models. Then testing of the model I think became much more difficult for them to be able to test. We had to give them some sort of staging or staging environment where they would build a newer version of the model, a better improved face recognition, for example. And then how do they test that, right? So be able to have the test data from either are like whatever the input weights were were used for the model, the input test data that was used, sanitizing that, using it again for a different weight of the model, stuff like that. So the whole cycle of doing ML deployments was fraught with challenges. That is, I think, one major in terms of other type. And then this time, I think the ecosystem was still maturing, or it is still, I think, maturing in terms of how do you run and deploy ML models in production constantly, right? I think that now there is so many platforms out there. I haven't gotten a chance to try out them but there are so many platforms that I see that they say, look, you write your models and we take care of deployment. And what I think they're trying to do is help with this whole process of being able to do it repeatedly, the testing, the deployments, the scalability of it and whatnot. So, but yeah, like it's something that's a very rapidly evolving space right now.
Thanks.